welcome back. So our next speaker is Alex Scott from Oxford. He will be telling us something about digraphs and tournaments. So Alex, is all yours.
Great, thank you very much. Well, thank you very much for this invitation. It's fantastic to be speaking here. I think the only thing that will be better would be to be there in person and actually giving in-person talk. But this is a good thing too. So I'm very happy to be talking at this workshop. So I'm going to talk about some joint work with Emil Pariasky, Michael Savory, and Elizabeth Wilmer. Emil and Michael are both PhD students in Oxford, and Elizabeth Wilmer is at Oberlin College in the US. Okay, so basically what I want to do this talk is, so I want to tell you about some results, and I also want to kind of mention some problems. I think there's some nice problems around these ideas, so some nice open problems. So that's really what I'm going to be talking about. So let's start with some definitions. So we have a digraph D, and take a set of vertices in D, and the process of inverting, so the inversion of X in D, you just take all the edges that sit inside X and just reverse their direction. Okay, so reverse the direction of every edge with both endpoints in your set X. Okay, and we're going to be interested in sequences of inversions that turn your digraph into an acyclic digraph, so you get rid of all the cycles. So we'll say that sets x1 up to xk are a decycling family of or for D if doing each of these inversions transforms D into an acyclic digraph. And one observation is that it doesn't matter what order you do the inversions in. So doing X and then Y is the same as doing Y and then X. Okay, so all that matters for a pair of vertices, if I've done a sequence of inversions, the only thing that matters is how many of the sets I've inverted contain both endpoints of the edge. Okay, so we never have to worry about the order. So we just think about a set of inversions. The other thing maybe to comment is that these are involutions. So if I do the same inversion twice, then I end up back where I started again. Okay, and then very naturally we define the inversion number of a digraph to be the minimum size of a decycling family. So the minimum number of inversions you need to do to get rid of all the cycles. And we'll say that a digraph is k-invertible if its inversion number is at most k. Okay, so those are our basic definitions. Okay, and there's been a kind of sequence of papers studying inversions. So possibly the first, there was in the thesis of Belkacin in 2009, and then there are papers of Belkacin, Boazes, Boadabus, and Puzet 2010, Puzet, Cador, and That from 2022, and a recent paper of Bang-Jensen, De Silva, and Havet. And actually, there are kind of interesting questions in all of them, but particularly this last one. So it was on, it's on the archive, and it's got a big list of interesting questions, and this is really what got us into it. We could have had a crack at some of these questions and answered some of them. Okay, so the talk's going to divide into two halves. There's going to be an extremal half and then an algorithmic half. I guess an extremal/structural half and then an algorithmic half. So extremal questions first, and again, you know, the first question you might ask is how large can the inversion number be? So if I have a directed graph on n vertices, then how large can the inversion number be? Okay, so let inv of n be the maximum of inv d over oriented graphs d of order n. And obviously we want to avoid digons. If we have edges in both directions, there's no way of getting rid of a cycle of length 2. So we're just thinking about oriented graphs here. Okay, and we're going to be particularly interested in oriented graphs and later on in tournaments as well. That's a very interesting special case. Okay, so a linear lower bound was proved by Belkacin, Boazes, Boadabus, and Puzet. So they proved that it's at least, the inversion number is at least n minus 1 over 2 minus log 2n in some cases. And the argument for that, so here's just the idea of the argument. It's just a counting argument. So think about n labeled vertices, 1 up to n. There are n factorial transitive tournaments on that set. Okay, and now if we think about starting from some tournament and trying to decycle it with k inversions, well, the number of choices for each inversion is at most 2 to the n. So the number of sequences of length k is at most 2 to the nk. Okay, so there's n factorial transitive tournaments, 2 to the nk choices of k inversions. On the other hand, there are 2 to the n choose 2 tournaments in total. And now you just do a little calculation. So it tells you that if k is sufficiently large to invert everything, then n factorial times 2 to the nk must be at least 2 to the n choose 2. Okay, and you do the calculation, n minus 1 over 2 is roughly where it bites. Okay, so a lower bound just a little under n over 2, about logarithmic, let me try this again, logarithmically much below n over 2. Okay. From above, the bounds are quite weak. Well, when I say quite weak, it seems likely that much better bounds should hold. So here's one easy fact. So inverv n plus 1 is at most inverv n plus 1. And you can see that easily. So if you take any digraph, pick a vertex, and then you could choose either the in edges or the out edges, say choose all the out edges, and invert the vertex and its out neighbors. That will reverse all the out edges instant with the vertex, and now you've made it into a sink. Okay, so with a single inversion, we can turn a single vertex into either a source or a sink, as we prefer, and now just work on the rest of the directed graph. Okay, so you've got, so you gain at most 1 in this extremal bound each time. Okay, so where do you start? Well, actually, we haven't thought about many examples, so let's think about 3 vertices. There are 2 tournaments on 3 vertices. And again, if you're doing worst case, you might as well think about a tournament, because you can always add in edges for free. There are 2 tournaments on 3 vertices. There's a transitive tournament, which has inversion number 0, because it's already transitive. And there's the cyclic tournament. And if you reverse any single edge of that, then you're happy. So the worst case then is a cyclic tournament, and that has inversion number 1. And now that implies that inversion number at n is at most n minus 2. Actually, some checking which earlier authors did. If you look at all tournaments on 6 vertices, it turns out that they can all be inverted with decycled with at most 2 inversions. So inv 6 is 2 by a case analysis. So that improves it to inv n is at most n minus 4. Okay, we can do a little bit better. So we improved it to about n minus log 2n. I'm not going to tell you about that argument. I think probably much stronger things are true. So we get this sort of teeny tiny bound, but at least it shows it's not n minus a constant. Okay, so the lower bound's about n over 2 minus a log term. The upper bound is about n minus a log term. So it's got a great big gap between the 2. Okay, but I hope this indicates the even, yeah, I mean, it's definitely a non-trivial problem. There is a conjecture for what the inversion number of n should be. So Berkogine, Buezes, Bradouis, and Pouzet conjectured a sharp bound. So they conjectured the inversion number of n is n minus 1 over 2 floor. I think we probably believe this conjecture as well. And they gave an explicit example that they believe it achieves the bound. So the tournament, you take a transitive tournament, you take a directed Hamilton path in the tournament. There's a unique one. You just go all the vertices in order, and you reverse just that single Hamilton path. Okay, so another way of saying it is you've got vertices from 1 up to n. All edges go forward, except edges between I and I plus 1 go backwards. Okay, so it's a very concrete tournament, and it seems kind of quite surprising to me that it's not easy to work out what the inversion number is for such a concrete example, but it seems it's not. So, and we don't know the answer. So, so the conjecture is there are other examples as well. It's conjectured that this tournament is extremal, but yeah, this bound's not known from either side at the moment. Okay, so I think it's a very nice conjecture. I hope this also illustrates, though, that even kind of very simple types of tournament, it can be quite difficult to analyze in this sort of problem. So it's actually quite interesting to see, okay, if we build up tournaments in simple ways, can we then at least control what's going on? Okay, so one very natural way to build up tournaments is to take, or digraphs in general, is to take a dijoin. So a dijoin is just you take two digraphs, you put all the edges between them and direct them all from left to right. So I've got digraphs L and R. I take disjoint union of L and R and add all edges from L to R. They're all pointing towards R. Okay, and more generally, if I've got a sequence of digraphs, D1 up to DK, I could do just the same thing iteratively. So I just line up D1 up to DK, and I put all edges from DI to DJ whenever I is less than J. Okay, and again, you can do that either just laying them all out at once or just by repeatedly taking dijoins of pairs. It doesn't matter which way you do it. Okay, good. Okay, so for example, let's think about the cyclic triple, which I'm going to call S, just because I've got various other letters floating around. So let's say the cyclic triple S. So we've seen that satisfies, that has decycling number 1. What if we take the dijoin of several copies of S? Okay, and Pusey, Kador, and that show that if you take n copies of the cyclic triple, then their dijoin has inversion number n. So we have this additive phenomenon. Each one individually has inversion number 1. You put n of them together, you get inversion number n. Okay. Right, so there's a question whether this holds more generally. So Bang-Jensen, De Silva, and Havet conjectured actually that additivity holds in the very general case that whenever you take two oriented graphs L and R, that the inversion number of the dijoin of L and R is just the sum of the two. By the way, it's clear that it's at most the sum of the two, because if I've got L and R, I can just work on L and decycle that, and then separately work on R and decycle that. Okay, so I know that the inversion number of the dijoin is at most the sum of the two inversion numbers. The question is the inversion number of the dijoin that large? Okay. Right, it turns out it's not, so we disproved this. So there's bad news and then a little bit of good news. So here's the bad news. So even for tournaments with inversion number 3, it's not true. So there's a tournament with inversion number 3, so that the dijoin of these cyclic triple and R only has inversion number 3. So it hasn't gone up by 1. So rather than 3 plus 1, it's just 3. Okay. So here's an idea. Let me just sketch the idea of the construction. So R is going to be built as a disjoint union of 3 sets, A, B, and C. And is the edges inside A, B, and C. A, B, and C are going to be interleaved in some complicated way. But inside A, inside B, inside C, the edges go backwards, and everything else goes forwards. Okay, so you could also think about it to start with a transitive tournament and invert the edges in A, B, and C. Okay, now I'd like to decycle R, but I'd like to decycle R and have a little bit of stuff left over to do something with S. Okay, so I've got the join of S and R. I want to do some operations on R, so it's going to turn out that the inversion number of R is 3 if we've constructed it correctly. What I'd like is that, okay, I can do this, but also do something on S at the same time. Okay, so I want to invert the edges in A, B, and C. Let's do it the following way. I'll do A union B, A union C, and B union C. Sorry, I'll invert the edges not in A, B, and C. So I'll invert all the edges between them. So the point here is that if you look at edges, say, between A and B, they're contained in A union B, but not in the other 2 pairs. So they do get inverted. On the other hand, if you look at the edges, for instance, in A, they're in both A union B and A union C. They've been inverted twice, so they're left unchanged. Okay, so the point is all the edges between A, B, and C have been inverted, changed direction. The edges in A, B, and C haven't been touched. Okay, so that decycles R. Okay, and here's how we extend it to S. So pick two vertices from S, doesn't matter which pair. S is vertex transitive anyway. And let's look at the set A union B union E, A union C union E, B union C union E. So just add E to all three of these sets. So we know that inside R we're happy. So it doesn't, we haven't done it, nothing will change inside R. What about inside S? Well, E belongs to all three sets, so it's reversed three times, good. So E has been reversed once, inverted once. And what about the edges between S and R? Well, if you look at the edges, say, between E and A, they're contained in the first two sets, but not in the third one. So they're left unchanged. And similarly for the edges between E and B, E and C. So we found a way of inverting R and separately, inverting some sets in R and separately inverting one set in S without doing anything to the edges in between. Okay, so that's the idea. You have to do a little bit of checking. Also, you need to interleave A, B, and C appropriately. So you have to check that in this process, somehow you haven't got some cheap way of dealing with R with two inversions or some other way of interacting things. So the simplest way of that turned out to be to interleave them appropriately and then do a computer check. Of course, you can check it by hand as well. And you can construct an example with R having 9 vertices as it happens. Okay, so there's a in the end relatively manageable construction. Okay, so that's the bad news. The good news is, well, in this example, we had R had inversion number 3, decycling number 3. So we can show that if you have a sequence of digraphs that have inversion number at most 1, then when you take dijoins, it does add. Okay, so the special case of the dijoin conjecture where all the digraphs have inversion number 1 is true. Okay, in fact, we can allow one of the digraphs to have inversion number 2 rather than 1. That'll be helpful later on. Okay, I'm just going to sort of indicate that the proof uses a characterization of decycling families. So I'm just going to flash a theorem in front of you, but just to give you, I really want, actually the characteristic vector is the main thing I want to mention. So if I have a sequence of inversions that I'm going to do, the characteristic vector is, it's sort of taking the transpose or kind of dual in some sense. You think about what happens at a vertex and you say, which sets do I belong to? You get a characteristic vector accordingly. Okay, so pick a vertex V, and then it's 1 or 0 depending on whether V is an xi or V is not an xi. So K, a sequence of K inversions gives me a characteristic vector of length K, and we'll work over the 2-element field. Okay, and whoops, then we have this theorem. Okay, I just want to point that it talks about decycling families, and it gives a characterization of when a family is decycling for the special case where all our digraphs have inversion number 1, a characterization in terms of characteristic vectors. Okay, so I don't want to dwell on this. I'm just saying that I just want to point at this being there. Okay. Okay, this proves this is enough to prove the theorem, and I just want to point at this useful fact at the end. So if the inversion number of each of the directed graphs is at least 1, then the inversion number of the dijoin of all of them is n, if and only if each one has inversion number 1. Okay, so remember I said if one of them has inversion number 2, then it still adds. This also follows out of this theorem. Okay, I just wanted to mention that because again, that's something I'll use a little bit later in the algorithmic part of the talk. Good. what have we shown? We've shown the inversion number is additive when all factors have d-cycle number at most 1, and may fail to be additive when one of them jumps up to 3. So we conjecture actually that 3 is the point where things get bad. So we conjecture that if all the digraphs have inversion number at most 2, then it's additive in that case. Okay, and that would sort of completely determine the picture in some sense. Good. Okay, let me talk about complexity. So there are also interesting algorithmic questions here. Okay, starting question, what can be said about the computational complexity of finding the inversion number? Okay, so let me just state the problem. So for a natural number k, the problem of k inversion, so the input is just you're given an oriented graph, and the problem is the inversion, decision problem is the inversion number at most k. Okay, so for example, zero inversion. So zero inversion just says I do no inversions and I'm acyclic. So in other words, is my starting digraph acyclic? And it's easy to resolve that in quadratic time. Okay, and you do need quadratic time because you need to look at all the edges, or almost all the edges. Okay, Bang-Jensen, Silva, and Havet showed one inversion is NP complete. So it's hard immediately. And they used the special case of the dijoin conjecture to show that 2 inversion is also NP complete. So essentially they considered take a digraph D and take D joined to itself. So they knew that if D had inversion number 1, then D arrow D has inversion number, so D joined to itself has inversion number 2. On the other hand, if the inversion number of D is larger, then that's not true. So they were able to show that 2 inversion is NP complete because, yeah, so it is D dijoined to G, D 2 invertible is equivalent to the conjecture, is equivalent to the question, is your initial digraph D 1 invertible? Okay. And they conjectured that NP completeness holds for all k, but they didn't have enough structural information to prove it. The dijoin conjecture would have proved that using kind of basically their idea. It turns out that the special case we proved, where all the components have inversion number at most 1, is also enough. Well, all the inversions have inversion, all the components have inversion number at most 1, or one of them has inversion number 2. Okay, and that those 2 facts together are enough to prove that k inversion is NP complete for every k. Essentially using just following their approach, but using the slightly more information that we had with our results in the dijoin conjecture. Okay. That's what I'm going to say about general oriented graphs. Now I want to think a bit about tournaments. Okay, so k tournament inversion is just what you expect. So the input is a tournament T, and the problem is the inversion number of T at most k. Okay, so k is fixed here, not part of the input. Okay, so there's been some thought about this, and one approach will be to consider critical subtournaments. So a tournament is k inversion critical if it has inversion number k, but any subtournament has smaller inversion number. Okay, and let's write I sub k for the set of k inversion critical tournaments. So, a priori it's not obvious that ik is even finite. Okay, so if you look at it for 10 seconds, it's unclear whether this is going to be a finite or infinite set. Okay. Let's note that a tournament has inversion number at most k, if and only if it contains no subtournament from ik plus 1 or ik plus 2. There's a little point here. So what happens if I delete one vertex from a tournament. So you might think this should just be ik plus 1. Okay, what happens if we delete one vertex from a tournament? So it's not obvious that the inversion number needs to drop by only 1. It might drop by 2. So it's at most 2. So let's think. Why is it at most 2? Well, I can, given a vertex, again I can take the out neighborhood. I could invert the vertex together with its out neighborhood, and that reverses all the edges out of the vertex. But it also reverses the edges in the out neighborhood. So I'll do a second inversion just on the out neighborhood. And now the out neighborhood is unchanged. So we've just inverted the edges out of the vertex. So certainly deleting a vertex isn't going to increase the inversion number by more than 2. The argument we had before that inv of n went up by at most 1, we were dealing with the worst case all the way through. So when we fixed a vertex, we didn't care what effect it had on the rest of the graph. So we didn't do that second inversion. We just said, take a vertex, take its out edges, invert vertex union out edges. Now it's become a sink. And now we do whatever we do on the rest of the graph. So we didn't care. Now we're being a bit more careful because we've got one specific tournament we're interested in. Okay, so it's certainly true that a tournament has inversion number at most k if and only if it contains no subtournament from ik plus 1 or ik plus 2. Just delete vertices until it becomes critical there. Okay. In other words, you get down to k plus 2, and either every vertex would reduce the inversion number by 2, or you find one and reduce the inversion number by 1. And that's the usual criticality sort of argument. Okay, right. So it turns out that ik is actually finite, and that was shown by Bang-Jensen, Bradabus, and Puse. So it was, I think, a compactness argument. So they didn't give there isn't an explicit bound on the size of this set, but it is finite. And it follows that if you think about the k tournament inversion problem, it can be solved in polynomial time for any fixed k. So for each k, there's just a list of k plus 1 and k plus 2 inversion critical tournaments, a finite list. And now you just have to check, do I have any of these tournaments as a sub-tournament? And that's polynomial time. I mean, that it might be very large because these tournaments might be large. Okay, so there's no particular bound on that, on the number or the size. Okay, so so it is solvable in polynomial time, possibly with some huge exponent. Okay, so Bang-Jensen, De Silva, and Havet worked further on this, and they used a different approach, and they showed that one tournament inversion can be solved in time, in cubic time, and 2 tournament inversion can be solved in time n to the 6. And they asked generally, okay, what do you actually need for a general k? Okay, and we were happy that we were able to answer this completely. So for any fixed k, k tournament inversion can be solved for n vertex tournaments in quadratic time. Okay, so it's always at most quadratic. The constant blows up with k, but it's always quadratic. And as a bonus, we get that if you have a k invertible tournament, then we can find an explicit decycling family for it. Okay, so it doesn't just answer the decision problem, it also comes up with a sequence that gives you the decycling family. Okay, and again, let's note that quadratic complexity is optimal as any algorithm must look at a quadratic number of edges. You have to look at most of the edges to figure out what you want to do. Okay. Okay, so let me, in the last few minutes, let me sketch the proof. And I'm not going to give you the proof in detail, I'll just sort of sketch a few ideas, like a very rough idea of the proof. Okay, so the first step is, we'll argue by induction. So the idea is let's delete a vertex from our tournament and apply the algorithm to the smaller tournament t minus v. Okay, so don't worry too much about the time. Basically, that takes quadratic time. We're then going to have an algorithm that does something else that time complexity can be controlled. Okay, so find a decycling family x1 up to xk for t minus v. If you can't, then you know that you're not your inversion number is more than k. And we can extend this decycling family to t minus v to a decycling family for t by adding 2 extra inversions. So remember, if we delete a vertex decycling number, we have this argument for decycling number dropping by at most 2. So we just take x1 up to xk and we add 2 new inversions just to fix the edges out of v. So 1 v and its out neighbors, 1 just the out neighbors. Okay, so now we're faced with a slightly different problem. We've got a sequence of k plus 2 inversions that decycles t. And the problem is now, okay, can I do it with k? But this sequence of k plus 2 is valuable information. So it tells us quite a lot about the structure of t. So we're going to think about t as a perturbation of an underlying transitive tournament t prime. In other words, we'll do x1 up to k plus 2, we get some tournament t prime. Let's reorder the vertices in the order given by t prime. So think about that as our sort of base order, and then the real tournament t we've got is there's some noisy version of this where we've done an x1 up to xk plus 2, which sort of messes it up a bit, but we think about t prime as our reference point. Okay, so a family y1 up to yk is decycling for t if and only if the family y1 up to yk and x1 up to xk plus 2 gives a transitive tournament when applied to t prime. Okay, so again, note that if we start with t prime, think about the effect of yeah, okay, I hope that's obvious. Okay, so right, so a family y1 up to yk is decycling for t if and only if the family y1 up to yk x1 up to xk plus 2 gives a transitive tournament when applied to t prime. The point is that you apply x1 up to xk plus 2, you get back to t, and now you apply y1 up to yk, and the order, of course, doesn't matter. Okay, right. So we want to determine when well, is there a family y1 up to yk that works? So here's kind of the key idea. So we're starting with t prime, and now we're going to do a bunch of inversions. K plus 2 of them I know what they are. K I haven't decided yet. But this whole business, it's enough to avoid ending up with cyclic triples. So if a tournament is not transitive, then it contains a cyclic triple. So shortest cycle has length 3. Okay, so all I have to do is avoid cyclic triples. So let's work in terms of characteristic vectors. So for each vertex, I think about the 0, 1 sequence of length 2k plus 2 that tells me, do I belong, am I in y1, am I in y2, ... am I in x1, am I in x2? So which ones do I belong to? Okay, so k plus 2 terms of that are just determined by x1 up to xk plus 2, which we know. But k terms are not, so the ones corresponding to y1 up to yk, those are up for grabs. Okay, so for each vertex, I'm going to end up with a characteristic vector of length 2k plus 2. Okay, and I'm thinking about it in the order t prime. So if I think about 3 vertices of t prime, let's say I less than, so uvw, say, so I less than j less than k, then I can work out whether or not I have a cyclic triple after my inversions by looking at the characteristic vectors. Okay, all I care about for my sets are, did I contain I, did I contain j, did I contain k? Okay, and that information is held in the characteristic vector. For each yi, for each xi, the characteristic vector tells me, for those 3 vertices, whether or not they belong to yi and xi. Okay, so there are good and bad sequences. So if I think characteristic vector u, v, and w for the 3 vertices in that order, I can figure out which sequences of 3 characteristic vectors are good, which sequences of 3 characteristic vectors are bad. Okay, good means I end up with something transitive, bad means I end up with a cyclic triple. Okay, those are the 2 options, what happens between 3 vertices. Okay, so what I actually want to do is construct a sequence of vectors without certain subsequences appearing. Okay, so what's my starting position? I have a sequence of n vertices in the order given by t prime. And for each of them, I've got some characteristic vectors I'm allowed, some I'm not, because the x's have told me that, okay, these coordinates of your characteristic vector are 1 or 0, depending on whether xi contains that vertex or not. Okay, so we have partially determined characteristic vectors at every vertex, but we can finish them off any way we want. So what we want to do then is we run through all the vertices, saying, okay, what possibilities are there? And we just want to avoid a certain set of subsequences of length 3. So it's become essentially a one-dimensional problem. We kind of run through the whole sequence. Maybe I'll put one more. We run through the vertices in the order given by t prime. And at each point, we track, at this point, what possible sets of subsequences could I have seen by this point? Okay, so it's sort of, it's one of these tree style arguments, but here just on a path. We track all possible subsequences of characteristic vectors that we could have seen, and then we iterate one step at a time. Okay. To the end, we then backtrack through the calculation, and that gives us an explicit sequence of characteristic vectors that works. Okay, and doesn't give any of the bad subsequences. Okay, if we survive to the end, we track back through the computation to construct a good family. And here's the good news: that computation takes linear time, because we're just running through one vertex at a time. We have a set of things we could have seen so far. The only information we have to keep is which subsequences we've seen. So we sort of possible sets of subsequences that we could have seen, we update them at each step. Okay. So that's a kind of rough sketch of the ideas of the proof. Let me conclude, and what I want to conclude is just to say that there are nice problems here. I think there's some nice things to think about. So on the extremal side first, so it's known that the upper bounds are on the inversion number are n over 2 minus, I mean the worst case inversion number, n over 2 minus a log term and n minus a log term, and the conjecture, remember, was that essentially n over 2 is correct. But I mean, even can we determine the limit of inversion number of n over n if it exists? I mean, that will be a good start. So is it closer to n or is it closer to n over 2? Here's another nice question. So we know the inversion number drops by at most 2 if you delete a vertex. Does every digraph with at least every non-trivial digraph, does every digraph have a vertex so that you can delete it and the inversion number drops by at most 1? So we don't know the answer to that. And then it's very natural to ask, what about random tournaments? So what's the typical inversion number? Okay. Yeah, we haven't thought too much about these, but I think they're nice questions. We thought a bit. Okay. On the algorithmic side, there's also a nice question, a nice conjecture. So we've shown that K inversion is NP complete for every K, and K tournament inversion can be solved in quadratic time for every K. Bang-Jensen, Silva, and Havet made the following nice conjecture. If K is part of the input, in other words, if you just ask what's the inversion number in effect, that is NP hard. So determining the inversion number of a tournament is NP hard. You can phrase that as a decision problem as well. I've phrased it loosely here. We believe we believe the conjecture, but we haven't proved it. So I think it's a nice question. Good, and I will stop there. Thank you. So thank you very much.
Yeah, let's thank Alex.